is a global grid, I think not too dissimilar to what SJ Lin talked about, that again can run at relatively high resolution, I think is as fine as 10 to 15 kilometers. Other models that we're working on and developing are regional models. There's an experimental version of the HWRF model that has been developed jointly at AOML and Esrel. It's based on the operational HWRF model. And it actually has the ability to run 3 nests now, or we're almost done developing that. And with that capability, we can run down to 1 kilometer horizontal resolution. So the hope is that, at least in sort of a research mode, we can do some examples of real-time runs at resolutions as high as 1 kilometer. So in terms of improved models, of course, you can have deterministic models and ensemble models, which we all know. Here's just an example of the types of fields you can get from a 1 to 1.5 kilometer grid length. So multiple models are used for this, the HWRF-X, the WRF ARW model, the AHW, COAMPS, various types of models, both regional and global. The hope is that eventually we'll have operational models running at grid lengths of less than 1 kilometer on the regional scale, maybe even hundreds of meters. And global models, ultimately, I'd say 1 kilometer. That might be several years down the road in terms of computing power. Ensemble-based approaches, of course, multiple runs with different initial conditions, as well as other ensemble generation techniques. Of course, it can provide indications of our forecast spread and uncertainty, as well as being used for data assimilation approaches. So just an example of multi-model and single-model ensembles, which we've all seen these types of plots. A multi-model ensemble showing you sort of a Poorman's ensemble, I've heard it called before, a way to get a sense of the forecast spread for a specific, in this case, Hurricane Ike, as well as several different realizations of the single model. So this is a FIM 20-member ensemble for Ike, again showing pretty decent spread that seems to cover pretty well the range of possibilities in this case for Ike. All right, improved observation. So one of the things that we do very well at HRD is we collect data. We go out and we collect data from aircraft in tropical cyclones. And so the 3 workhorses of our observational fleet include our 2 NOAA P3s, which have tail Doppler radar capabilities as well as dropsonde capabilities, flight level data, SFMR, which is surface wind speed and rain rate. Those are all very important instruments that we use to collect data from the P3s. The G4 is another aircraft that we fly. We've had that for about 12 to 15 years or so. And so similar to the Dot Star, that flies at high altitude in the environment with tropical cyclones, releasing dropsondes, which are then used for improving forecasts of hurricane track. Remote sensors include, again, the Doppler radar, SFMR I mentioned, scatterometers, and then ultimately, actually this year we're hoping to test another type of unmanned aerial system called the Coyote. But we've also used an aerosonde, which is a platform, an unmanned system that flies at very low altitude, as low as hundreds of feet above the surface, in a tropical cyclone environment, regions where manned aircraft just cannot safely fly. So these are the types of platforms and observations that we are doing, currently do, and planning to do in the very near future. So the types of observations you can get, well, one of the things you need to do for intensity forecasts is the multiple scales. So you can look at a vortex scale observation. So this is an example of a flight track that we flew in, I believe, Katrina. And so here's what the wind field looked like from the airborne Doppler. So this is, again, showing wind maximum on the northeast side, and then looking at a vertical cross-section across Katrina, the 3-dimensional wind field we can get, the tangential wind on both sides of the storm, as well as the radial wind. So you can see that at this time, there was a significant asymmetry, wave number 1 asymmetry, in terms of the radial flow field with Katrina. Boundary layers are another example of the type of observations that we're starting to really develop the capability of looking at. So you can look at, for example, turbulent kinetic energy estimates from the airborne Doppler right underneath the aircraft. And we can see things that look like the possibility of boundary layer holes from the airborne Doppler. So this is some pretty new data that we've really started to look at now, and I think it shows a lot of potential for improving our understanding of boundary layer processes, and especially in landfall and tropical cyclones. Okay, now improved use of observations and models. So one of the things that we're working on in partnership with others, for example, Fuqing Sang at Penn State, as well as the capability in-house at HRD we've developed now, is a data assimilation of intercore observations using an ENKF and ensemble Fallon filter. So we use an ENKF assimilation of airborne Doppler radar data. So this is an example or a cartoon of what the data looks like from the P3 from the tail Doppler. So it sweeps in the vertical around the aircraft as it flies through the storm. So this is what that sweep geometry looks like. And then we could take that data and provide a means by which the modeling community or the assimilation community can sort of intelligently average that data to generate what we call superobs, SOs, superobs. And then that data can then be used in an assimilation mode using an Simon-Kalman filter for the model to hopefully produce better forecasts. So just an example of that, one of the things that we've been doing at HRD is developing the ability to test different strategies for the airborne Doppler. And to do that, you really need to develop what we call an OSSI, an observing system simulation experiment. So in this case, we actually ran an experiment where we ran a very high resolution simulation of a hurricane. And then we developed a way to synthetically sample from that simulation and look at what the, am I running out of time? Okay. So we wanted to look at ways that we could sample the data from that simulation and then assimilate that data into a series of runs to see how well that data that's assimilated from the nature run that we call it leads to improvements in the structure and intensity of the storm. So here's an example. So we have the nature run, again, which is a very high resolution model. And then we have a control run where we did not assimilate any data, and then an analysis using the assimilated data. And what you can see, this is sea level pressure, is that by assimilating this data using an ENKF technique, we get a much better central pressure reading as well as a wind field compared with what we got from the control run. And finally, looking at the structure of the storm, you can see that the structure from the runs using the assimilated data shows the structure of the storm is much closer to what we're seeing from the nature run in terms of both the radius of maximum wind and the amplitude of the secondary circulation. Another thing that we want to do is to improve our visualization of both the model and the observations. So this is a way that we are also improving our use of observations. This is a flight track of a P3 flight into Hurricane Bill, I believe, from last year, showing the winds at flight level in that hurricane. So then we're developing ways that we can overlay, for example, this is the Doppler-derived winds at flight level from our flights into Hurricane Bill. And then this is a way to look at the model output. So this is a model forecast valid at the same time. So these types of visualization techniques, I think will really help us to better diagnose how well the forecast is doing, as well as hopefully improve forecasts in the future. Another way that we can improve, I think, models is by developing new model diagnostic techniques. This gets at Russ's comment about sort of structure-based or feature-based diagnostics from the models. So this is just a radius and height plot of axisymmetric winds from, I'm just going to look at this bottom row here. This is Hurricane Katrina. This is from the airborne Doppler data, so you can see a maximum of about 30 kilometers, RMW. And then these are two different model runs at different resolutions, a 9-kilometer and a 3-kilometer run. And what you can see is that the 3-kilometer run does a better job at getting the structure of the storm in terms of both the radius and maximum winds as well as the slope of the eye wall with height, better than the 9-kilometer. So that's just an example of the kind of things you can do. And finally, looking at turbulence scale diagnostics, you can look at things like taking very high resolution observations from the P3 and looking at things like theta profiles and sensible heat flux profiles within the boundary layer. You can compare different model profiles with what we get from our observations to do things like improve representation of fluxes in the models. So to improve our predictions in the future, again, it will require three things: improved observations and